All right, 3.3 has three titles, right? We're going to look at three different sets of formulas. So if you have your formula sheet in full, there will be three different blocks of formulas on those. They're in your notes, of course, here as well if you've printed those off. So they're called double angle formulas, power reducing formulas, and then half angle formulas. And so the first set that we're doing are double angle formulas, and they're sort of drawn across the page if you've got the notes printed, but here there's not enough space, so they're drawn a little bit differently. So what you see happening on this one is every angle is double of theta in the middle on the left, right? So sine of 2 theta, cosine of 2 theta, tangent of 2 theta. And once again, when we have this tangent of 2 theta, this formula may or may not be how you actually want to do it. If you've already found the sine of 2 theta and the cosine of 2 theta, it might just make sense to divide sine by cosine and not actually use the formula. But there are instances, too, when this would be particularly helpful. So these are the different formulas we have. And you'll also notice that tangent of 2 theta has three different formulas you can use. So depending, again, on the context would depend on which one you might want to use. For example, if you're trying to find the tangent of 2 theta and you knew the tangent of theta, that first formula is really helpful. But if you were given only cosine, you wouldn't want to use that one, right? So it's kind of nice that they give you some options of different ways this can present itself in different contexts to make it easier to work with. Okay, so we're going to take a look at a triangle that's given to us. The triangle that's given to us has an angle alpha in the triangle, right? But we were asked to find the sine of 2 alpha. Now, generally speaking, we still may need to find the third side of the triangle, all right? But that doesn't mean we just look at the triangle and then we can just find sine. We still have to use those double angle formulas because this triangle is not a triangle with a double, like a 2 alpha angle in it. So let's start with finding what the sine formula is. So if you take a look back on the previous slide, what does it say that the sine of 2 alpha is? So we're going to have 2 at the beginning, right? And then we're going to have the sine of the angle and the cosine of the angle singular, right? Not double the angle, but the original singular angle. So this is 2 at the beginning, and then sine of alpha and cosine of alpha. That's helpful. And the reason it's helpful is because my triangle is in terms of alpha, not in terms of 2 alpha. So looking at this triangle, you can apply all the things that you already know about sines and cosines, right? Like opposite, hypotenuse, adjacent, all that kind of stuff. But in order to do that, we are going to need to know the hypotenuse. So how do I find the hypotenuse of this triangle? Let's just review old hat stuff. What do you got to do? Pythagorean theorem. So we'll call this side C. So we have 7 squared plus 24 squared equals C squared. 7 squared is 49. What's 24 squared? If you have a calculator now, would be a great time to get it out. You're going to need it for a lot of the things we're going to do potentially. 576. And then if we add these together, what are we going to get? 625. And what is the square root of 625? Yeah, it's 25. So our third side is 25. That also means that 7, 24, 25 is a Pythagorean triple. We've talked about those in passing a couple of times. It just means all the side lengths are whole numbers. Not all that doesn't always happen, but this one is one of those. All right, so looking at this triangle then, what is the sine of alpha? So the 2 stays at the beginning. The sine of alpha is 7 over 25. What is the cosine of alpha? 24 over 25. Okay, everybody good? And now we're going to simply multiply some things out. Notice nothing reduces. 7 over 25, 24 over 25, those are in simplified form. The 2 in the front doesn't reduce with either of the 25s in the denominator. So this is just like 2 over 1. So if you multiply all the numerators together, what are you going to get? I told you you're going to want a calculator today. 336. And the denominator you probably know from work already on the screen. What is 25 times 25? 625. So this would be the sine of 2 alpha. Notice, We don't know what alpha is. We don't know what 2 alpha is, and we don't need to, right? Nobody asked us to find the angle measure. So be careful. Just because there's a variable in a problem doesn't mean that you're like trying to solve for a variable, okay? So we are finding the sine of 2 alpha here. It's 336 over 625. Okay, let's try another one. Okay, directions say use the given information to find the exact value of each trig function. And this time it tells us the cosine value. It doesn't draw a triangle. It tells us that the cosine of theta is 4 over 5. And it tells us that theta lies in quadrant 4. So we need to draw our triangle in the right location. And the reason that we do is because sometimes negatives show up depending on which quadrant we're in, right? So we want to be careful if there's a negative involved that we find it or identify it. So we're going to draw this into quadrant 4. I'm going to draw my sketch over here. And quadrant 4 would put us down here, something like this. So my theta would be right here. Did you say down this? Yes. Cosine is adjacent over hypotenuse, so adjacent would be 4, hypotenuse would be 5. This is a familiar to us triangle. If you don't recognize it, feel free to use the Pythagorean theorem, but you probably recognize it, many of you anyway. Do you know what the third side would be in this triangle? It's a 3. Yeah. So a 3, 4, 5 Pythagorean triple is here, so there is a 3 here, but is it really 3? Yeah, it's a negative 3. So we need to make sure that we've got a negative on it because we are down in quadrant 4, right? The y value is negative. Very good. So sine of 2 theta, we've written this one already in the previous slide, so I'll write it again. It's 2 sine of theta, cosine of theta. Okay, so using the triangle, we actually know cosine, they gave it to us as 4 over 5. What is the sine of theta in the triangle that we drew? Negative 3 over 5. Okay, opposite over hypotenuse is negative 3 over 5. And then once again, there's no reducing that can be done. We're going to multiply across the top. 2 times 3 is, times 4 is 24 and negative. And then 5 times 5 is 25. Okay, now we're going to do cosine of 2 theta. Cosine of 2 theta. I know that's what I don't know how I didn't get that fixed. I'm so sorry. Okay, let me do this real quick. These are alternate forms for cosine. They're right in your notes if you've got them printed. They're wrong on my screen. This happened last semester, and I thought I fixed this one. I need to make a change to this slide. I apologize. These are alternate forms for cosine, not alternate forms for tangent. That's what happened when it shifted something that it wasn't supposed to be shifted. I apologize. Okay, so we have 3 different formulas for cosine. Okay, so erase everything from your mind about what I said about tangent. We have 3 different forms for cosine. You get to pick. Do you want to do the first formula, the second formula, or the third formula for cosine? So we have 1, here's option 2, or option 3. It doesn't matter. We just need to pick one. 3? Okie dokie. We're going to do the third one because Chloe's the only one who's going to talk to me today. Okay. Chloe decided we're going to do number 3. It's 1 minus 2 sine squared theta. So this is 1 minus 2 sine squared of theta. All right. The 1 and the 2 are there. What's the sine of theta? Negative 3 over 5. And we're supposed to square it, right? We're squaring sine. This is not squaring theta, it's squaring sine. So it actually loses the negative when we square it, right? So this is 1 minus, I have 2 times, and then I'll have 9 over 25. What is 2 times 9 over 25? 18 over 25. And then you can get a common denominator. You can use your calculator to subtract it and change it, doesn't matter. I have 25 minus 18, which gives me 7 over 25. So we have negative 24 over 25, and we have 7 over 25. Okay, is everybody good?
Would 25 over 25 be negative 2? Because it would be 1 minus 2, which would be negative 1.
Say that again, Beck.
The 25 over 25, would that not be minus 2.
Right, but this one just turns into 25 over 25. One's a positive number, so 25 over 25 is a positive number. Yeah, I'm just moving it down, like vertically down instead. Yeah. Okay. There's a third one on this one. I think I have a third slide. Yep, tangent of 2 theta. So we have a choice. For tangent of 2 theta, we can either go back to this formula right here, which we could totally use if you'd like, or we can divide sine divided by cosine. What would you guys like to do? Okay, Lydia says sine divided by cosine, so we're going to do that one. Okay, so tangent of 2 theta is sine of 2 theta divided by cosine of 2 theta, both of which we found in parts A and B. Sine of 2 theta was negative 24 over 25. Tangent of 2 theta was 7 over 25. Okay, so we've got a fraction inside of a fraction, which would happen if we had done the other formula as well, by the way. We'd still have that, nuance going on. And then we don't want fractions inside of fractions, right? We don't leave them like that. So the way that we will divide by a fraction is that we will multiply by its reciprocal. And what lovely thing happens? Yeah, the 25s both cancel, right? On the diagonal, which leaves me with the 24 on top, negative, of course, and the 7 on bottom. Okay, is that all right? And, of course, if everything has been done correctly, this formula right here that we didn't use should give us the same thing if we had used it, right? I actually think it's a little bit messier on this particular one because we've got the 1 minus part in the denominator. But pause for a moment and consider, if they hadn't asked us A and B, it might not be very useful to use sine of theta over cosine of theta, and using the formula might be more beneficial, right? Yeah, so there's benefits to it having it, but not necessarily that we would use it all the time. Okay, now let's take a look at one that we can actually find from a different perspective. So on this one, we actually have angles given. Yes, ma'am? Oh, I'm sorry. You bet. You got it? Okay. Sorry, moving too fast. This one, we actually have angles given, right? Pi over 12 is in there. But if you remember your unit circle, which I really hope you do at this point, pi over 12 is not in it, right? It's not. But what we're trying to do in general is what we did in the last section when we saw a weird angle like 105. What we tried to do in that section is say, okay, well, are there two numbers I can add or subtract to get 105, right? That's what we were doing. The same idea is present here. In this particular set, we're taking a look at it and saying, okay, pi over 12. And you're welcome to turn it into degrees, but it's not going to be a very nice one, okay? I mean, it's not going to be one you're going to know, I should say it that way. What we want to do is we want to see, well, can I double it and get an angle that I am familiar with? So let's just check real quick so that you can see that it will work. If I take pi over 12 and I double it, what do we get? Yeah, it's pi over 6, right? 2 pi over 12 would reduce, and then we'd get pi over 6. Shake your head because that's a familiar one, right? That's a unit circle value that we know. So if you take a look at the pieces and how they're set up, 2 tangent of pi over 12, 1 minus tangent squared of pi over 12. This is the right-hand side of the trig identity right here, isn't it? It's the right-hand side. So I can move from the right-hand side back to the left-hand side. And the way that I do that is that I take the angle, pi over 12, and I double it on the left-hand side. Does that make sense? So I'm going to take, in a very real sense, a pi over 12 is here, and a pi over 12 is here, and a pi over 12 is right here, and 2 times pi over 12 is what's on the left-hand side. Now, that's the pi over 6 that I just found. Okay, so I take this, one more, and I can rewrite it. I'm rewriting it sort of backwards of the order, but this is the tangent now of 2 times pi over 12, or likewise the tangent of pi over 6. Now, sines and cosines are a little friendlier than tangents, but if you'll remember, and we'll just draw it out real quick, we're at pi over 6, which is the lower value down here. What's my ordered pair here? Good. And Chloe got them in the right order. So x is the larger one here, square root 3 over 2, and then 1/2. How do I find tangent? Sine over cosine. So which of these is the sine value? The first one or the second one? The second one. So it's the 1/2 divided by, let me write that out. We're going to do the sine of pi over 6 over the cosine of pi over 6. If you don't want to write it, that's fine. But just to remind you, that's what we're doing. So we have our 1/2 here, and then we have our square root of 3 over 2 here. And then how do I find this? Well, multiply by the reciprocal. What happens when I do that? I get 2 over 2 square roots of 3, or the 2's cancel before that, either way. So now I have 1 over square root of 3. Rationalize. Good job. So square root of 3 over 3, square root of 3. So now I have square root of 3 on top. And what's square root of 3 times square root of 3? 3. 3 on bottom. And remember, no canceling the 3's because one's an inner radical and one's not. So just so you know, I don't think you really need to show anywhere near this many steps, but I want you to see they're coming from where they're coming from, okay? And if you were to look back at this later, like on a video or whatever, I don't want you to be unclear as to where we got them. Okay, is that good? Okay, next set of formulas. So those are the double angle formulas. The next ones are called power reducing formulas. There's not multiple versions, so this slide's correct. So this tells us what happens when we have a squared power. Now, like sine squared. You might just say, well, why don't we just find sine and square it? And you still can, right? Like, of course you can. But there are instances where this is going to be helpful for us. We'll see some of them. But these are formulas that are established. In particular, for those of you who do need more math beyond trig, if you're taking to Calc 2, we use this particular set, not a lot of the other ones, but this one is used heavily in Calc 2, okay? So there are places where further along we come back to some of this earlier stuff in trig and it really matters. This is one of those places. We're going to do some other things with this semester, though, before you ever get to Calc 2, for those of you who do. And we're going to use these kind of formulas in particular when we're doing some solving of equations in 3.5. So what we're going to do is we're going to take a question like the following, and we're going to use the power reducing formulas to change the cosine power. But the cosine power here is to the power of 4. And you can't go over here and just remove the squared and put a 4 and move all the 2's into 4's. Like, you can't just change all the 2's to 4's. That would be lovely. I wish we could do something like that. That'd be so nice. Doesn't work that way, right? Like, all of the things that we sometimes wish would be true just don't always work, and this is one of those. It's going to require a little bit of work for us to get the 10 cosine to the power of 4x to actually be in single powers of cosine. That's why you got so much space on this particular page if you've printed them out. This is a long problem, okay? I think I even have, no, I didn't. I have one slide because I can make it smaller as I go. All right, so here's what I want you to recognize first. Let's just think of it in terms of if I just had x to the 4th, okay? If I had x to the 4th, that's the same thing as having x squared squared. That's a property of exponents, right? Okay, that's the first property that I'm going to use here. And the reason I'm going to do that is because if I can get this in terms of something squared, then I can use these properties, right? I want to be able to use these properties because these properties allow me to power reduce. So I'm going to take this value that I'm given and I'm going to rewrite it. The 10 in the front's fine. I'll leave him there. And I'm going to rewrite this as cosine squared of x squared. Okay, I'm squaring something squared, that's to the power of 4. This is now in the form in the middle here where I can use these formulas. And it tells me what I'm going to do. It tells me that the cosine squared is 1 plus cosine 2 theta divided by 2. I end up having to double the angle when I do it, right? 1 plus cosine 2 theta divided by 2. So now we have 10. I have 1 plus cosine of 2 theta. Whoops, sorry. Divided by 2. There we go. Squared. Okay, just doing a replacement, right? I need to square the top, I need to square the bottom, but when I square the top, please do not make the mistake of squaring each individual component. When you square with addition and subtraction, you FOIL. Okay? I'm going to jot this down aside and remind you that a plus b squared does not equal a squared plus b squared. It's not a fact. What you have to do is you have to write down a plus b times a plus b, and you FOIL it out. And if you do, you get a squared, you get a 2ab, and you get b squared. Okay, that's the pattern that shows up when we FOIL this out. The 2 on the bottom squared is fine. I can distribute that down there. So I'm going to regroup this a little. I'm going to put the 10 on the outside, and I'm going to put a 4 on the outside because that's 2 squared. And then I'm going to write out that I have 1 plus the cosine of 2 theta times 1 plus the cosine of 2 theta. So I kind of merged at least a couple steps into that single one. Do you have any questions about that step?
Wait, how did you just move the 4?
So what I did is I separated the fact that this is squared like this. Let me just erase the parentheses. And I said I'm going to square the top and I'm going to square the bottom, which is the same thing. So yeah, and then I just shifted it out with the number because it's not going to require any foiling because it's single by himself on bottom. If there was addition on bottom, I'd have to do the same thing, but there's not. Okay, let me put that back just so that it looks cleaner where it was before. Okay, 10 over 4 will reduce. I can reduce that at least to 5/2, so I might as well do that at the moment. And then we're going to FOIL this out. Now, I showed you sort of how we think about the foiling, but we're going to take it a step by step because with trig it looks a little bit different than when algebra. So when I multiply my first terms together, that didn't work very well. Let's try again. We have 1 times 1, so there's 1. My outer terms, I have 1 times cosine 2 theta, so that's plus cosine of 2 theta. My inside terms, I've got another plus cosine of 2 theta. And then my last terms. So what happens when I multiply cosine of 2 theta times cosine of 2 theta? It's squared. So this is now cosine squared of 2 theta. But the directions said what? What about powers in the directions? What's that? It doesn't contain any. Is that what you said? Yeah, you're right. It doesn't contain any powers, and this one still has a power of 2 right here. Right? It says no powers greater than 1. We want no powers greater than 1. Yeah? So I need to do this thing that I just did again. I'm going to go ahead, I think I'm going to go ahead and distribute the 5/2 through so that it cleans up the beginning part of it. We're going to get messy somewhere along the way. So I think I'm going to go ahead and make it cleaned up at the beginning and get it messy as we keep going. So I'm going to distribute my 5/2. So this is 5/2 times 1. What happens when I combine cosine 2 theta and cosine 2 theta? Yep, so I've got 5/2, and then I've got 2 cosine of 2 theta. Can you see how that's going to simplify? What's going to happen when I multiply 5/2 times 2? I just get 5. So here's my 5/2 down here. Here's actually just 5 cosine of 2 theta here. And we still need to work with the back piece. So over here now I have 5/2. And it's cosine squared of 2 theta. But I know how to power reduce cosine squared. In fact, I've already done it once on this screen. Cosine squared is 1 plus cosine 2 theta over 2, right? That's the formula. So my 5/2 will stay in front. I will have 1 plus It's supposed to be the cosine of 2 theta, but what is my current angle in the problem I'm working with right now? It's already 2 theta. So what will my new angle be at this point? 4 theta. I need to double the angle, whatever the angle is, right? If the angle were 30, it'd become 60. Well, this angle is 2 theta, so it's going to double and become 4 theta. And it's divided by 2. Now, in terms of the directions themselves, we've done everything they've asked. We just need to clean things up. Like, I don't have any powers of cosine left at this point. They're all singular. And I've got no space. So let's see what I can do about that. Okay, that'll work. So I have the 5 halves in front. I have the 5 cosine of 2 theta. And then I need to distribute and clean some things up over here. So this 5 will go through the top, right? And this 2 will go to the bottom. So we have 5 plus 5 cosine of 4 theta over 4. I think I got all the pieces. Does that look right? Yeah, looks good. There is one more thing I can do to simplify and clean this up. Does anybody see what it might be? There are 2 5s. The 2 5, well, there's lots of 5s. Which 2 are you looking at, JC? In the fraction. The 2 5s right here. I can't combine them because one's multiplied by cosine. Okay, what else do we see that we might be able to do something with?
Can we bring out 5, like the common?
Well, if we did, we would just be putting it back the way it was before, which doesn't end up getting us, it just kind of does a circular reasoning thing. These are all good suggestions, right? Keep thinking. What else? Yeah, there is some fraction addition we can do. Can somebody be a little bit more clear? There's something we need to do before we can do that, though.
Do you make it all just one fraction?
You could get common denominators and make the whole thing one fraction. That's one option. I think there might be another option as well.
Is it the cos 2 theta and cos 4?
So we won't be able to combine the 2 theta and the 4 theta cosines. Those are not going to be able to be manipulated.
5 cosine 2 just be 10 cosine.
It's not, right? 5 cosine of 2 theta, if you go back to that first slide that we had about angles that are the double angles, it's not, you can't just pull it out. So we could make everything into a fraction. Let me show you the better option. You ready for it? Okay. You guys are all thinking really good things. If you put it all into a single fraction, it would be okay. That would be an option. I think it's probably a little bit easier if we take this and we separate it into 2 separate fractions, though. So I can separate this as to 5/4 and 5/4 cosine of 4 theta. Does that make sense? Right? Addition on top, I can separate into 2 separate fractions. And then do you see something that we can add together? Yep, the 5 halves and the 5/4. So at this point, this piece and this piece can be combined. 5 halves and 5/4. They do need to have a common denominator, of course, right? So if I think about that, let me underline them instead. This one multiplied by 2 and 2. I'm going to have 10/4 on the first one and 5/4. That's going to give me 15/4. And then they don't actually look much like fractions anymore because I've put the coefficient 4 for the denominator in front with the 5. So a couple of you were saying, can't I just make a common denominator on all of them? You could. If you made a common denominator on everything, it would look like this when you combined it all. You'd have a 15 here, you'd have a 20 cosine 2 theta here, and you'd have a 5 cosine 4 theta here, and it'd all be over 4. So this would be another perfectly reasonable conclusion. But can you see it looks a little messier than the one that we came to? It's not wrong. I mean, they are both simplified versions, but from a little bit different perspective. Okay? Where does the 4 come from on the cosine at the end?
Yeah.
So fractions, I'm dividing each of these pieces by 4. The 4 is in the denominator there.
But I mean in the cosine for angle.
Okay, so remember that came about from over here. When I take this formula and I double the angle, if I have an angle 2 theta and I double it, it becomes 4 theta. So whatever the angle is, and it gets doubled, I have to double that, right? So if this had a number in it, like 45, and I had to double 45, I'd get 90. This isn't a number. I mean, like it has a portion of it's a number 2 theta, but when I double 2 theta, I get 4 theta. And that's coming about from this formula that says whatever this is, I double it, and I get twice as much on the right-hand side. Okay. These are messy. Yeah? So keep asking questions because I'll answer multiple times even if it's still confusing, okay? How are we doing? Maybe that's not a fair question at the moment. I'm not sure. Okay. We have one more set of identities. They're half angle identities. And I think they're probably the ugliest ones that we have because of 2 reasons. Number 1 is the square root. But number 2 is that there's a plus or a minus in front of them. And you might be thinking, well, why is there a plus or a minus? And the reality is because when you half an angle, sometimes it changes it from a positive trig value to a negative trig value. In particular, if you think about, we'll do one that's cosine. If you have a cosine angle that's like 120 degrees, right? Cosine in quadrant 2, it's negative, correct? But if you half 120 degrees, you get 60 degrees. Now you're back in quadrant 1 where all the trig values are positive. Are you with me? So that can happen, but it doesn't have to happen, right? Some of the angles, if you half them, nothing happens like that, right? If I were already in quadrant 1 at 60 degrees and I halved it and I'm at 30 degrees, all the signs stay the same. So this takes a little bit more care to make sure that as you take a look at it, you actually end up in the right place with the right sign. Now, if you don't know what angle inside you're in and whatever, then you just leave pluses or minuses in front of them and we're good to go. That's actually the easier option. But that's why the pluses or minuses are there, is because it can change the sign. Okay? And you do see 3 formulas for tangent, and those actually really are 3 formulas for tangent this time, even though I screwed up the earlier slide. Okay? 3 formulas for tangent. And they're kind of friendlier, the ending 2, than the beginning one. It doesn't have the plus or the minus on all of them, and it doesn't have a square root on all of them. Okay, so we're going to take a look at one where we actually know the tangent or the angle value for tangent. 112.5. What quadrant am I in here just as a reference? Yep, we're in quadrant 2. Everybody good with that? Cool. But aside from your calculator, which of course can give you an approximation for tangent 112.5, you don't have an exact formula from a unit circle for 112.5, right? Okay, so let's think through the things that we've done so far. Earlier, like in 3.2, a couple class periods ago, we said we could add a couple things together or subtract a couple things and we could get 112.5. Well, that's not helpful, right? There's no unit circle values that we know that when we add them, we get a 0.5 or we subtract them, we get a 0.5. So those addition and subtraction ones are out the window. They don't work for this. The double angle formulas that we got early on, that doesn't help us, right? If I were to take this and I'm trying to think of it this way. Oh, and then let's use it. We actually might be able to use the double angle formulas. Oh, but because we're starting on the left-hand side. So we're on the left-hand side. If I have tangent of 2 times this, and I would have to do it in half in order to get to the right-hand side, I actually get 112.5 divided by 2. That's worse in terms of a decimal, right? I get a smaller decimal. I get a 0.25 decimal. So I can't use this formula either, right? The tangent formula here doesn't help us. Okay? Where were we? There we go. So we would really actually like to take that 112.5 and double it instead. Because if we take 112.5 and I double it, what do I get? 225. Now, that's not maybe our favorite angle in a unit circle, but it's one of them. Where is it? Yeah, this is in quadrant 3. Do you know which angle it is in quadrant 3? Yeah, it's the one that's halfway, right, Chloe? So it's down here like this. Okay, pretty good. So when I double this particular angle, I do switch quadrants, which means my signs on something might not be the same as they were in the previous quadrant, depending on which trig function I'm looking at. The one I'm looking at here is actually tangent. Which of the, well, let's write this down first. Do you remember what this ordered pair is right here? Uh-huh. Excellent. So we've got a couple of negative square root 2 over 2 kind of values. Okay, so if I'm using my formulas here, I can use any 3 of those formulas at the end. I can use the one that has cosine only with the square root and the plus or minus, and I'll get a negative because tangent is negative in this quadrant. Or I can use the one that has the sine and the cosine in it, where sine's on top, or the sine and the cosine in it, where sine's on bottom. So would somebody like to pick one for us? You want to do which one? The first one?
Yeah.
Okay. So Beck's wanting to do this one. Chloe is not convinced that this is the best choice, I can tell. We can do it though. You ready? Okay. If you don't want to do this one, do a different one, and we can confirm that we all get the same answer. That's super fun too. Okay. All right. So we're going to do the first one. We are in quadrant 3, so we will have a negative value, right? Tangent is negative in quadrant 3. No, I'm sorry. I said that wrong. Positive. We will have a positive value. Tangent is positive in quadrant 3. So I'm going to have a positive value for this. I'm going to put a plus there to remind you. We really do have a positive here. And then I'm going to have 1 minus the cosine of alpha and 1 plus the cosine of alpha. We may abandon this very quickly if we don't like it, but that's okay. We could do that too. Okay, so what is our cosine value with the unit circle pieces that we just identified? Negative square root 2 over 2. And we have 1 plus, and we have another negative square root 2 over 2. As we clean this up, we are going to run into a slight problem by using this formula. Does anybody have an idea what problem we're going to run into that's really kind of messy on this one? They don't cancel out. That would actually be really friendly if they did. I wish that were the case. Taking the square root of a square root. Do you guys see that? There's square roots inside of square roots. That's really difficult to work with. So I'm going to backtrack, and I'm not going to let you pick number 1 back. Are you okay? Okay, sorry. You will get to a point where you won't be able to simplify. It's going to be the problem, and you're going to see square roots inside of something. You're going to be like, this is not giving me the right answer. There's got to be a way to simplify this, and there's not a very nice way to do that. All right, so we're going to backtrack. Somebody pick 2 or 3. I promise 2 and 3 will both work. 2. Sine alpha over 1 plus cosine alpha. Okay. So we have our sine value. Oh, I'm sorry. Our sine value. What is our sine value here? Negative square root 2 over 2. And then we have 1 plus, and what's our cosine value? Negative square root 2 over 2. All right, so we don't want to have the radicals on bottom, and we don't want to have the fractions inside of fractions. There's 2 issues to deal with. The issue I'm going to deal with first is the fractions inside of fractions. Do you see that both of the little fractions have the same denominator here, a 2? Because that's the case, we can actually multiply by 2 over 2, and we'll be able to eliminate the fractions. Now, it might be more helpful for you to actually write down that we're going to multiply each piece of this by 2 instead of writing it the way I originally did, because that's what will happen when you distribute the 2 on bottom. So on top, I end up with negative square root 2. On bottom, I end up with a 2 at the beginning and a minus square root 2 at the end. Okay, is that all right? How do I get rid of 2 minus square root 2? This is not the kind of rationalizing that we see the most of the time in trig, but it is something you've seen before in algebra.
2 plus root 2.
Very good. Does anybody remember what it's called when you multiply by this thing that looks similar with a different sign in the middle? Not reciprocal. Good guess. Reciprocal is when we flip something. Starts with a C. It's conjugate. Very good, Shaylin. Okay. So when we multiply and we want to get rid of a radical on bottom, there's addition or subtraction. We always want to multiply by what's called the conjugate. The conjugate is the exact same pieces. So it's 2 in the square root of 2 with the opposite sign. And the reason that that works is because, well, it's because of differences of squares. So we're going to FOIL it out to remind you because we don't see this happen on most of our problems. But let's do the numerator first. It's the simpler of the two. So we're going to take our negative square root 2 and we're going to distribute this through. So on top I have negative 2 square root 2. And then I have minus, and then what's square root of 2 times square root of 2? Square root of 4, which is 2. Yeah. So that's the numerator. It cleans up with just a single step. Let's actually FOIL out the denominator, and then I'll sort of cut to the chase of how you can think about it in the future. So if I FOIL out the denominator, the first terms, 2 times 2 is 4. The outer terms, 2 and square root of 2, would be plus 2 square root of 2. The inner terms, what do I get? Actually, this one's minus. Minus 2 square root of 2, the opposite, yeah. And then the last terms, what happens when I multiply negative square root of 2 times positive square root of 2? You get a 2 and it's negative, yes. Okay, everybody good? What happens to the square root terms here? They cancel out, and they always will. That's why you did the conjugate, okay? So if you do the conjugate and you do that with the right perspective, what you should know is that when you move from this denominator that said 2 minus square root of 2, and we multiplied it by 2 plus square root of 2, that I just need to multiply the outside terms together. 2 times 2 is 4, right? I'm sorry, not outside, the first terms together. 2 times 2 is 4. And the last terms together. Negative square root of 2 times positive square root of 2, and I get negative 2. Okay? So what I end up having here at this point is negative 2 square root 2 minus 2 over what? Over 2. And what do you see happen next? There's 2's in every single term, okay? The square root 2 part doesn't matter, but this 2 and this 2 and this 2 cancel, and all the 2's become a 1. I don't want you to think that it canceled out to a 0, especially at the end. It matters. Technically, the one on the denominator doesn't really matter because it doesn't affect the value. But at the beginning, I have negative square root 2, and then I have minus a 1. Did I get that right? I think so. The signs in my notes are one, I'm off on something. But I don't think that we're off. I think we're okay. All right. What do I have left? Okay, I have one more problem left that's like this, so we're going to do it, and then we'll do the verifying ones for next time, and we will postpone the due date. And as a reminder, again, if you wait to start this and you're going to have 2 assignments due between Monday and Wednesday, which is your choice to do, you did it to yourself, okay? So I would encourage you to start this assignment over the weekend, even though you're probably not going to want to finish it. We've seen this triangle before today, a 724 triangle. Do you remember what the third side was? It was 25. So I'm going to write that in right here. We already know this side. The sine half angle says the following. It says that I have plus or minus, I have the square root of 1 minus the cosine of alpha over 2. That is alpha, but why isn't it working? There's alpha over 2. So we're asked on this problem to find the sine of alpha over 2. So we're going to find this. Because this is being drawn with positive values for all of these, right? Do you see 24, 25, and 7 are all positive? We're already in quadrant 1, right? And so if I half something that's already in quadrant 1, it will stay in quadrant 1. Nod your head if that makes sense. Right? If something is less than 90 degrees and you divide it by 2, it's still going to be something between 0 and 90 degrees. So this one really is just the positive value on this one because of the location of the values being positive to start with, No other place does that happen. So we're going to take a look at doing 1 minus. What is the cosine value of this triangle? Oh, these are badly. Does it say theta in your notes? Yeah, it should say alpha. Change the triangles to say alpha. My screen does, but your notes don't. I'll get that fixed too. What's the cosine value? Sorry. 24 over 25, you bet. And that's all divided by 2 under a square root. So let's clean some things up. Obviously, the fraction in front side of a fraction, not ideal. We eliminate that by multiplying by the denominator that's there. This is one way to do it anyway. So I'm going to eliminate it by multiplying by 25. So that's going to give me 25 minus 24 over 25, right? Or sorry, over 50. So this one distributes to here to be 25. It distributes here to cancel, and then I get 50 on bottom. What's 25 minus 24? 1. So we have 1 over 50, okay, square root. We can simplify this as square root of 1 and square root of 50. What's the square root of 1? That's 1. 50 breaks down. How does 50 break down? 25 and 2. Yep, and then those are 2 5s. So this is 5 square root of 2. And then to simplify the square root of 2, we multiply top and bottom. So we have square root 2 on top, and we have 10 on bottom for this one. Okay, everybody good? Awesome. So if you're taking a look at what can I do on the homework, the only thing we haven't done here is the verifying identities part. We've done everything that has computational pieces, anything, just the things that don't say verifying identity, that's where I'd pause.